Hi, we're now at the halfway point of our contest. We're doing Chapter 7 on nuclear reactions, and this is the 7th lecture. So up until now, we've actually looked only at radioactive decay, and we're now going to consider the energetics and some of the other problems that are associated with actual nuclear reactions, which are reactions that are going to look something like this. We start out with one nucleon, which we're going to call the target nucleon. And we're going to actually bombard this with a particle, or it could also be, in some cases, it might actually be a photon, but usually it's particulate. And this, we're going to call this the projectile. And that's going to give rise to some product. So this will be our product nucleon. And then there's going to be an emitted particle. Not all the time, but most of the time. There'll be an emitted particle or a photon. So this is the general form of what we call XY type nuclear reactions. So we've got a projectile and an emitted particle. Now, there's also the possibility, and this happens not infrequently, that sometimes there'll actually be an intermediate, what we call compound nucleus that's formed, and it'll be in an excited state. So we can actually have something that looks like this. So C is our compound nucleus, and then C is just going to decay to B plus Y, plus Y. So an example would be, for instance, if we're dealing with a nuclear reactor, we have the fissionable isotope uranium-238. It could be, we could put this into a nuclear reactor. It's not fissile. It's not something that we can make nuclear weapons out of. It's not good for using to power a nuclear reactor. But one of the things that we can do is we can put it into a nuclear reactor that's already producing a lot of neutrons. And these things are called breeder reactors. We put in a certain amount of uranium-238, and we can make a fissile isotope of plutonium out of it. And that's going to look something like this. So again, our target nucleus would be uranium-238, and our projectile, in this case, is actually going to be a neutron. And we're going to make this compound nucleus, which will be uranium-239. And that's not going to be around very long. And it's just going to give us a new element called neptunium. And it's going to do that by beta decay. So it's going to have to give off a beta particle. And you'll notice 93 minus 1 is 92, and 239 plus 0 is 239. So this goes to neptunium. Neptunium is further going to decay, also by beta decay, to plutonium, which is 94, 239, plus the beta particle. So that just gives you an example of the kind of reaction that's shown on page 119. Now, when we're dealing with the energetics of these things, there's something that we want to calculate to find out whether this reaction is actually producing energy, or in some cases it might actually require the absorption of energy in order for that to occur. And that's going to depend upon whether or not when we actually look at the masses of the reactants and the masses of the products, it's going to depend on which is greater, the reactant mass or the product mass. So for instance, if we add up the masses of the individual reactants, and an example that's given in your book on page 120 is the reaction of a isotope, common isotope of vanadium, which is vanadium 51, with absorption of when it's irradiated with neutrons. So we're going to take vanadium 51, and we're going to irradiate it with neutrons, and it's going to give us vanadium 52 plus a gamma photon will be produced in the process. Well, the gamma photon doesn't have any mass. It's not going to change either its atomic mass or atomic number. So this is basically, if we wanted to write it, it would be 0, 0. We don't need to do that, but that would actually completely balance this. Now, if we want to actually look at this value that we're going to calculate, this energy value, which we call Q, the Q value is actually going to be equal to the difference between what we're going to do is we're going to look at the energy of the reactants and the energy. We're really looking at the mass of the reactants and the mass of the products. So if we add up the mass of the reactants, that is in atomic mass units, we add up the mass of vanadium and the mass of a neutron, that's going to equal, and then we subtract from that the mass of the products. We're going to get the difference in mass, once we convert that back into energy, is going to give us the Q value. So this is how we do that. We add these up, we get 51.952,629 as a sum of these two reactants, and the single product that has a mass is 51.944779 atomic mass units, and the difference between the two of them, the difference in mass, is going to be equal to 0.007850 atomic mass units. We just use U to abbreviate atomic mass units. Okay, we also know that there's 931.5 million electron volts per U. So if we multiply that times 0.007850 U, use the mass units cancel out, and we're going to be left with an answer of 7.312 million electron volts. So this is the energy that's produced by this actual reaction. Okay, so what can we do with that? Well, first of all, it tells us that since this is the energy that's being produced by the reaction, we know that this reaction is exergonic, or your book uses a word which is a little strange, which is exoergic. Both of these words are equivalent. I prefer the term exergonic, but they're both exactly the same. And the opposite, which is endergonic, which would be endoergic in your book. If this has a positive sign, then that would be, Q would be, if Q is positive, then the reaction is exergonic or exoergic. If it's negative, it's endergonic or endoergic. So whenever we're dealing with things like a decay, it's always exoergic. It's always exergonic. It always gives off energy. But for nuclear reactions, they may be endergonic or exergonic. They could be either way. So I just want you to keep that in mind. Okay, there's another example that's given in your book, which I want to get into. Well, actually, no, it's the same. No, it is. I'm sorry, it is a different reaction. It's actually a very classic reaction. It's a reaction that was performed by Ernest Rutherford in 1919. An interesting reaction where he actually took nitrogen. That was the target nucleus. And he bombarded it with alpha particles. Now, what actually happens here is we do get a compound nucleus. It's not shown in the initial reaction, but I'm going to put it in anyway. So we're going to get a compound nucleus out of this. And the compound nucleus, because we're going to see this later on anyway, is actually fluorine 18. that's going to go on to the products, which is oxygen 17. And that being the case, the other product has to be a proton. Okay, so with this information, we can do, with what we've got so far, we can actually do some calculations that will enable us to actually draw an energy diagram for this particular set of reactions. So the first thing we're going to do is, as we did before, is we're going to calculate Q for the reaction. And the way that we do that, again, it's going to be, what we're going to do is we're going to look at the mass of the reactants. We're going to subtract from that the mass of the products. The mass of the reactants, in this case, it's the mass of nitrogen plus the mass of helium, and that gives us a total of 18.005677 atomic mass units. Then we're going to take the mass of the products, oxygen 17 and the hydrogen atom that's formed, and that gives us 18.006957. Now in this case, we're going to get a negative number when we take the reactants minus the products, and we're going to find out that the Q for this is actually going to be equal to minus 0.001280 atomic mass units. Not the Q, but the mass difference, I'm sorry, the delta M. And then if we actually convert that into Q, again, where we're going to take the delta M and multiply it by 931.5, it's going to be 931.5 times delta M, and that's going to give us a value of, that was in atomic mass units, this is MeVs, million electron volts per atomic mass unit, and that gives us a value for Q of minus 1.19 million electron volts. So that is an endergonic reaction. And what we can do with this is we can calculate something called the threshold energy. This is going to take into consideration not only what we've done so far, but also we're also going to take into consideration changes in momentum that are going to occur as a result of these reactions. So we can say that the threshold energy, which is E sub TR, is going to be equal to minus Q times the value A sub A, which is the atomic mass of A, which in this case would be the nitrogen, plus A sub X, which is the atomic mass of the helium. That's our projectile, divided by A sub A. And when we do that, we substitute everything in there. We get, for Q, we've already calculated that. Minus 1.19 is plus 1.19. So we're going to have 1.19 million electron volts times 14 plus 4, that's 18 over 14. And when we put all that together, we're going to find out that that's going to be equal to 1.53 million electron volts. This is what we call the threshold energy. Now, if we were using as our projectile, if we were using a neutron, this is all we would have to do. We would have gone far enough just by doing this. But in fact, let me see if I can move this a little bit here. I'm not getting, for some reason I don't seem to be getting the entire board in there. Okay, that's a little bit better. Bring this up here. Okay. If we were, as I said, if we're using a neutron, this would be fine. This would, we could stop right here, but we've got another consideration now. Since we're not using a neutron, we're using an alpha particle, and it's a positively charged particle. In fact, there's a little wrinkle that's put in here, and that's the fact that whereas a neutron doesn't have any charge, and a neutron can easily approach the positively charged nucleus without a problem, since in this case our projectile is positively charged, there's a repulsive force that is acting between the proton and, between the alpha particle and the protons that are in the nucleus of this nitrogen atom. So there's this Coulombic repulsion that we have to overcome, which is called the Coulomb barrier. And we have to have enough energy to be able to overcome that Coulomb barrier. So we actually have to modify this a little bit. We've got another equation that we're going to use to take into consideration this Coulombic barrier. And we call this the effective Coulomb barrier. And the formula for that is, I'm going to erase this now, but we're still going to use part of that formula in the next equation. I probably shouldn't have erased that. No, it doesn't matter. We don't need this anymore. So I'm going to put the effective Coulomb barrier in here. And that's going to be equal to, approximately equal to, 1.11 times the A sub A plus A sub X over A sub A times, again in parenthesis, Z sub A, Z sub X over A sub A cube root of, so that's to the 1/3 power, plus A sub Z to the 1/3 power. And if you look at all the terms that are in here, of course this is the atomic mass again of the, for our particular reaction, that was the starting material, the nitrogen. This was the projectile. Again, the atomic mass of nitrogen. Z are the atomic numbers for nitrogen and the projectile. So this is 7. For the projectile, it's 2. So this will give us 14 on the top. And then this is going to be down here. This is going to be the cubed root of, what is the atomic mass of this? It was 14. It's the cube root of 14 plus the cube root of 4 for helium, for the, and then this is going to be what it was before. 14 plus 4 is 18 divided by 14 times 1.11. So if I've done that correctly, we should actually get, when we do all of that and actually carry out the calculation, we'll get a value of 4.95 million electron volts when we do this. Okay, so that actually is giving us this effective Coulomb barrier. And since the alpha particle that fortuitously that Rutherford used was an alpha particle that actually had quite a bit of energy in it. It's the alpha particle that comes from the decay of an isotope of polonium, polonium-214, and it's a 7.68 MeV alpha particle. Since its energy is considerably greater than the effective Coulomb barrier, it's enough to actually cause this reaction to take place. Okay. A couple other things that we can get out of this. We can get something called the kinetic energy of the compound nucleus. So remember I did say that there was a compound nucleus that forms in here, and the compound nucleus was this fluorine, it's 9, it should be a 9, fluorine 18. So if I want to see what its kinetic energy is when it forms, I can use this equation. I've got another equation here. This is equation 7.4, and this one says that the energy, kinetic energy of the compound nucleus is approximately equal to the kinetic energy of the projectile times the quantity A sub X, which is the atomic mass of the projectile, divided by A sub C, the atomic mass of the compound nucleus. So in this case, that would be the energy of the projectile was 7.68 million electron volts times A sub X over A sub C. A sub C is 18. A sub X is 2. No, I'm sorry, it's 4. It's helium. It's 4. So it's 4 over 18, and that gives us a value of 1.71 million electron volts. Okay. Okay, so that is the energy of the compound, the kinetic energy of the compound nucleus. If we could assume that all these things that we formed are in the ground state, and we wanted to find out how much energy is produced or consumed. So what is Q for the overall reaction? Q would be actually equal to the mass of nitrogen, which is our target, the mass of the proton, of the helium, and we'd have to subtract from that the mass of the products, and we would multiply that by 931.5 million electron volts per mass unit, and that's going to give us a value of the Q value for this reaction is going to be equal to positive 4.41 million electron volts. Now, what else can we do with that? Well, if we take those two values and add them together, we can actually find out what the excitation energy of the excited fluorine 18 nucleus is. And if we can do that by taking the energy value of the alpha particle that was emitted, the 7.68 million electron volts, add to it the Q value that we just calculated, the 4.41 million electron volts, and then we have to subtract from that the energy, that negative 1.71 million electron volts that we calculated, which was the kinetic energy of the compound nucleus. And if we do all of that, we find out that the overall energy there is 10.38 million electron volts. So we can actually take all this information and we can make a very nice decay diagram out of it. Not a decay diagram, I'm sorry, but an energy diagram. So we're going to do that as we did for the decay diagrams. We're going to show energy here, and that's going to be in MEVs. And over here, we're just going to show various. We're going to show first of all our reactants. Now this will be the energy of the reactants in the ground state. So ground state reactants are going to be over here. And then our products are at a slightly higher energy, so we're going to put them up over here. So this is the ground state of the products. And now we get to put in our fluorine. First of all, we can show the fluorine 18 in the ground state. And we can also show the fluorine 18 in the excited state. And we can now actually label this with all the energy differences. These are the values that we actually calculated already. So remember we calculated this one value, which is the difference between the reactant ground state and the fluorine ground state, and that was that 4.41 million electron volt difference that we had. That's the one energy. The energy that we just most recently did, which was the 7.68 plus 4.41 minus 1.71, that was the 10.38 million electron volts, is the energy difference between fluorine in the excited state and fluorine in the ground state, fluorine 18, 10.38 MeVs. And there's one other one that I haven't shown yet, and that would be the difference between the ground state of the reaction and the ground state of the products. That's right here, and that's going to be equal to 1.19 million electron volts. And I think that was the first, if memory serves me correctly, I think that was actually the first number that we calculated. That was, let me see. All right, so this gives us an energy diagram for that reaction. These things are very, very useful for actually visualizing what's actually going on here. There's another example that's given in the book that's asking you the minimum energy required to convert plutonium-240 by alpha bombardment to curium-243. And that also produces a neutron, and we do that in exactly the same way that we've done before. We look at the mass of the reactants, we add up plutonium and helium, we get 244.056410 atomic mass units. We add up the curium and the neutron, we get 244.070047 atomic mass units. We find out again that this is endergonic. It's minus 0.013637 atomic mass units, converting that into from mass to energy with 931.5 million electron volts per mass unit gives us minus 12.7 million electron volts. That is the Q value for that reaction. It's endergonic. We can then calculate the threshold energy, which is 12.7. It's going to be 12.7 million electron volts times 240 plus 4 divided by 240. So the threshold energy for that reaction is 12.9 MeVs. And we're also going to have to look at the Coulomb barrier, and that's 1.11 times 244 divided by 240 times 94 times 2 divided by the cube root of 240 plus the cube root of 4, and we wind up getting 27.2 MeVs for that reaction. So it's a very, very high, the Coulomb barrier is very, very great for that.